Good morning, everyone, and welcome to a new episode of Loops by Belta. In this episode, we are going to explore how waste from electric and electronic components and the data about them can enable their recovery so that Europe can be more strategic autonomous on the availability of critical raw materials. With me in this session, I have three different European projects, one represented by me, which is even closer, and we will go there later, but I have different guests. So first of all, Giulia Lattoni from FutuRaM. Then we have connected with us Marek Vasilevsky from the project METIUM, another i3 project. And then we have Anastasia Maria Moscovi, which is joining me from the Even Closer project as a company, exemplifying what the businesses are doing here. And me, myself, I am Luca Polidori, and I'm happy to moderate this session with you. We will have a lot of time to discuss things, and I do not want to spoiler everything in the introduction, so I will quickly jump to the first presentation and leave the word to Giulia from FutuRaM, which will give a presentation on data-driven insights on CRMs in waste from electronic and electronic components. Thank you, Giulia.
Thank you, Luca. Thanks, first of all, for the invitation in being part of this webinar and for your interest in the FutuRaM project. Today, I'd like to discuss with you indeed how FutuRaM data can contribute to improve the knowledge and ultimately also the recovery of critical raw materials and strategic raw materials from WEEE. Let me just know if the presentation is moving correctly, but it should be. So just a few words about myself. My name is Giulia Iattoni, and I'm part of the Cycle program, which is under the United Nations Institute for Training and Research Divisions for Planet. What we do in our team can be summarized in three main pillars. Research and statistics, mainly but not limited to WEEE quantification. We do this at global and at regional level. We do also capacity building and trainings on e-waste statistics and on e-waste management. And we also provide policy advice. For example, now we are supporting the European Commission for the review of the WEEE directive, which is upcoming. And we're also supporting in the context of the CRM Act. And we are part of global partnership concerning e-waste. So just starting with a short overview, quite general on the project. First of all, the meaning of the acronym FutuRaM is future availability of secondary raw materials with focus on strategic and critical raw materials. The project started in June 2022 and will end in May 2026. So at the moment, we are at the very last stage, let's say. The consortium, it is composed by 28 partners from different 11 countries, and is part of the Horizon Europe Research and Innovation Program, indeed. So here you can see all the logos of the institutions involved in the project. So what's the background where the project is moving? The European Union is aiming to strengthen the resilience of raw material supply chain in order to enable the green and digital transition. And a key objective for this is to reduce the current over-dependence that we are having on third countries. And to achieve this, somehow the EU is promoting increased domestic production of both primary, but also and importantly, secondary raw materials to recycling from waste, with, again, a strong focus on critical raw materials. And although the Critical Raw Materials Act was adopted after the FutuRaM project was already being launched, the project is strongly still aligned with the core objective of the CRM Act, thanks to a close collaboration and exchange that we are having. So within this background, we immediately face two challenges. First, that at the moment there is no structure and harmonized knowledge on the availability and recoverability of strategic and critical raw materials from WEEE. And second, that there is no central knowledge base where to receive and retrieve this information. And this kind of bring a downward spiral, what we call, because when data are missing or are of poor quality, then decisions are based on bad information and leading to weaker policies, reduced funding, and ultimately even worse data upcoming. So I would say that the two main goals and outputs as well of the FutuRaM project are first to enable fact-based decision-making for secondary raw materials management in the EU27+4, because in the analysis we are including also United Kingdom, Switzerland, Norway and Iceland. So that's why we say +4. And this should be done through developing knowledge on the availability and recoverability of secondary raw materials, with the special focus on the strategic and critical raw materials, not just for now, but up to 2050, so with a forward-looking approach as well. And second goal is then to disseminate this information through a secondary raw materials knowledge base, which should be accessible to everyone. So I just like to specify that today we are focusing on WEEE, but FutuRaM has a much broader scope actually and covers many more waste stream type. So batteries is one, then we have vehicles, slag and ashes, mining waste, and the construction and demolition waste from building and wind turbines. So you can imagine the wide scope actually of the project. So taking now a look at the method and some results on the amount of strategic and critical raw materials in WEEE. As first step, I will be brief concerning the methodology, but I think it's also important to mention. So as first step, in the FutuRaM methodology, we developed the product composition for 54 different product groups, following the UNUK's classification. The composition data is built according to a hierarchical and nested structure where we start from the analysis at product level, then we identify the components which are embedded in the product, the materials embedded in those components, and the elements embedded in those materials. So each layer is linked and mass balanced also with the upper and with the above one. And the data for this have been obtained mainly from product sampling of recyclers and PROs, which we have as partners in the project, and literature to fill also some gaps. So this is just to provide you with an idea of how our composition is structured, and that's the example for the product laptop, which is part of the screens and monitors category as defined in the WEEE directive. Then we apply a stock and flow model to quantify the three main indicators of e-waste statistics, which is the amount of product placed on the market, the stock, and the WEEE generated. We apply a sales lifetime approach for this, quantifying first the amount of products being placed on the market. And for this, we start from the trade and the domestic production statistics. And then we apply a lifetime profile to derive the WEEE generated. And consequently, we can also derive the product in stock. The stock and flow model is applied for a very long time series, and it is strongly rooted to the principles of the official e-waste statistics. And out of the amount of WEEE generated, we know that part of it is being collected compliantly with the legislation, while part is destined to other complementary flows. For example, this is mixed with other plastic and metal scrap and undergoing substandard recovery. It can be mixed with the residual solid waste, it can be exported, or it can also go to undocumented fate. And data for this mapping were obtained mainly from Eurostat, but also from other sources like the key figures published by WeForum, and also some national studies that we could obtain from the member states. So through the stock and the flow model that we apply, then we can also derive the composition of the waste, which maintains the same hierarchical and nested structure as the product composition, but is not anymore at product level, and rather at category, aggregated at category level as defined in the WEEE directive for the reporting, and also shifted in time. because the composition of the waste that is being generated in 2020 depends on the composition of the product that were placed on the market before then. So, for example, in 2010, 2012. So that's why we have this shift in time to be considered. And this is just an example for category 2, screens and monitors, as defined in the WEEE directive, but we are having the same for all categories, temperature exchange equipment, lamps, PV panels, and so on, for each year and for each country in the scope of the project. Then the last step of the methodology was to quantify the amount of secondary raw materials recovered and lost during recovery, and this was done through a recovery model, where we mapped and quantified the flows throughout the main treatment processes using data from producer compliance scheme, from recyclers, and also from literature. And this is just an example for the copper content in category 2, screens and monitors, and is also an extreme simplified flowchart just to provide you with the idea behind it. But we have this type of analysis for all critical and strategic raw materials that we analyzed and for all the categories as defined in the WEEE directive. So the entire methodology was then applied for 3 different future scenarios because the project needs to develop data set up to 2050. So we consider 3 different future scenarios: business as usual, recovery, and circularity scenario. In the business as usual scenario, we assume that the current trends are being continued in the future, mostly unchanged. In the recovery scenario, we assume to have improved waste collection and recycling, so better waste management and treatment. And in the circularity scenario, we assume to have improved waste collection and recycling, same as in the recovery scenario, but also accompanied with a reduced consumption, which means less products placed on the market and eventually also less waste generated. So as outlook to 2050, what we could see is that the WEEE generation increased from 8 million tons in 2010 to 10.7 million tons in 2022, and is projected to grow at an accelerated rate under both the business as usual and the recovery scenario, reaching 19 million tons in 2050. In contrast, the circularity scenario is projected to result in a lower regeneration of 12.5 million tons after having a peak around 2040. And this decline is mainly attributed to product lifetime extension through reuse and repair, and also by reduced consumption, which are the 2 main assumptions under the circularity scenario. However, even in this case, some WEEE categories, such as photovoltaic panels, are still expected to grow, even when we analyze a circularity scenario. The total WEEE generated in 2022 contained 29 strategic and critical raw materials, each present in quantities above 1 ton. And these equated a total of 1 million tons of critical raw materials in 2022. And this projected to grow to between 1.2 and 1.8 million tons by 2050, depending on the scenario that we are considering. And the most abundant elements that we could find were aluminium, copper, manganese, and silicon. But then there are also many others, as we can see. And there are also some significant declines that can be observed for some critical raw materials in particular. And that's, for example, the case of antimony, that was used in cathode ray tubes, which have been phased out from the market, but also the case of other rare earth elements like yttrium, cerium, europium, lanthanum, and so on, which are being used in the fluorescent powders used in fluorescent lamps, which have also been phased out gradually and recently. So we can see the decrease most evidently in the circularity scenario, but quite evident also in the business as usual and in the recovery scenario in respect of the 2022 observed data. So having now a look at the WEEE management in the EU27+4, out of the 10.7 million tons of WEEE generated in 2022, only 5.7 million tons, which is equivalent to 54%, were collected and appropriately treated in a compliant way, which means in accordance with the EU regulation and the WEEE directive. And these volumes were collected through retailers, municipal collection points, and commercial collection companies, or any other official means, let's say. Then, following treatment, approximately 0.4 million tons of critical raw material were successfully recovered, including copper, aluminium, silicon, tungsten, palladium, but also precious metals such as gold, silver, and also other type of material like steel and other ferrous metals were also recovered. Nevertheless, despite a compliant collection and treatment, still 0.1 million tons of critical raw materials could not be recovered and were lost during the process. And this is the case mostly for rare earth elements like neodymium, dysprosium, yttrium, which are present in small quantities but are vital materials found in permanent magnets, fluorescent powders, and other components. Then out of the total we generated, the remaining 46%, which means about 5 million tons, was not compliantly collected or treated, increasing the chance of losing valuable materials. And the largest quantity falls under non-compliant recovery, including WEEE that is being mixed with metal and plastic waste, where only some materials such as iron or steel maybe could be recovered, but often at lower standards. And then another part is discarded with the residual solid waste and sent to either landfill or incineration, depending on the country. And a fraction is also exported, and then the remaining share is undocumented, which means likely either exported illegally or processed through informal or unregulated channel. And this led to 0.5 million tons of critical raw materials lost during the collection phase even. Then just to showcase an example for one strategic raw material, based on the FutuRaM data, copper can be found in many WEEE categories, and that's the case especially for small equipment, large equipment, and temperature exchange equipment, while in terms of components, that's the case for printed circuit boards, for cables, for compressors, and for inductors. That's just an example, but we have the same analysis for all strategic and critical raw materials as a result of the project. And here you can see the amount of copper recovered and lost during collection or treatment in the U27+4, both in 2022 and in 2050 for the three different scenarios. So in 2022, we had around 170 kilotons of copper recovered and around 190 kilotons lost. And then considering higher collection rate, improved separation of copper-rich fraction by 2050, depending on the scenario, we could reach between 320 kilotons of copper recovered and 530 kilotons of copper recovered, again, depending on the scenarios that we are considering. This is just the example of copper, as I mentioned, but we have this type of analysis also for all the other strategic and critical raw materials. So I just gave you a short snapshot of the results that we're having so far in the project, but if you're interested in more detail, I invite you to consult this report, which is accessible to the QR code here, that we published in conjunction with the International Waste Day, last 14th of October 2025, that was released. And here you can also see a nice video that accompanied the media campaign of this report, which was reported in more than 900 online news items and mentioned in several different languages. In case you're interested not just in the results for WEEE, but also for other waste stream, you can also consult the Urban Mine platform, which is the data hub, let's say, that we are publishing all the results of the FutuRaM project. And this was launched in November and is now available for everyone and for the public. Then I'd like to just mention a few words on what's next for FutuRaM. In the future. In terms of project achievements, what I would like to say is that in FutuRaM we managed to obtain the first integrated quantification of waste generation, composition, and critical raw materials availability to 2050 across multiple and complex waste streams. We develop harmonized modeling approaches, which could be applied consistently across the EU27+4. We managed to integrate many heterogeneous data sources into a coherent data set, and we brought also some methodological innovation and modeling advances, including with transparent and documented assumptions. And we developed tools and data set that can be reused, updated, and improved in future work according to the FAIR principle. Here there is also the link to this another repository that we are using, where we are publishing all the milestones and the reports, the deliverables, the data set produced in the project, which is also accessible for everyone for transparent documentation. Then in terms of policy impact and next step, the dataset from FutuRaM have been so far used for mapping critical raw materials rich components and waste streams for Article 26 of the Critical Raw Materials Act, and this work was done in conjunction with the JRC. The dataset are also being used for the impact assessment for the recast of the WEEE directive, which is ongoing. And then we are going to have the final project report in May 2026, and after that we hope to get even further national uptake. So in the end, the goal of FutuRaM, the main goal of FutuRaM is moving from the downward spiral that we saw at the beginning to a kind of, let's say, more virtuous cycle, where basically we have high quality data that enable better information that can support stronger policies and more targeted funding. And this in turn also improves data quality in the end and leads to higher recovery of secondary raw materials in Europe. So to conclude, I just invite you to stay tuned to the project through the FutuRaM website, through the Urban Mind platform if you want to see the results. You can also get involved as part of the stakeholder network of the project, and you can also contact us directly. So thank you for your interest, and back to you, Luca.
Thank you, Julia. Very, very interesting results brought from the project. I was also during the Critical Raw Material Week at the launch of your project's platform, but thank you for having explained in such a detailed way the methodology. Now it's clear how these numbers got there for me. So, and I will not take much time now because we will have half an hour after the three presentations, but I do have some questions already in my mind that I want to ask you. I just take the opportunity to remember everyone, the people invited, so also the other projects, and the public at home, that if you have a question, you can leave it in the comments and we will tackle it later. Now, from one project which is almost at the end stage, like the one we just saw, to a project that I believe just started. I think the METIUM project is ready for its presentation. I don't know if Marek, you can, yeah, I see you on screen. So please, Marek, the floor is yours.
Okay, thank you very much. Yeah. Yes, this is the first slide. Thank you for being invited for this seminar. As you mentioned, the METIUM project is already started. We have a kickoff meeting of this project at the beginning of the December last year. So we are very, let's say, fresh, if we can say at this words. And the METIUM project, which is called Hydrometallurgical Tech for Interregional Urban Mining, was developed under the call of I3, Interregional Innovation Investment Instrument. And as I said, we will start our activity at this moment, and this project will take for the next 3 years for their implementation. What is about the METIUM project? METIUM project is let's say the first kind of this project which is built the interregional urban mining ecosystem in Europe. And we will develop 4 cross-border strategic raw materials value chain by scaling up 15 demonstrators from collection, dissemination, pre-processing to finally to the hydrometallurgy, which is given on the slide here on the right side. We see the four line for, let's say, value chains for the to develop, as I said, in this 4 processing activities: collection, dissemination, pre-processing to hydrometallurgy, the different part of the materials. And our METIUM project, as I said, to build the first interregional urban mining ecosystem in Europe, linking with less development regions, which is the very important issue, and innovators recover strategic raw materials through advanced hydrometallurgical process, which are already set. So our activities is not only focusing on the 4 cross-border strategic raw material value chains, but also to build this what we called hydromet triangle. The hydromet triangle, I will develop all of this, what I'm talking about at my first slide in my whole presentation, but would like to mention that hydromet triangle, this is 5 pilot plants from the different parts of the Europe, providing a green alternative to pyrometallurgy, which is, everybody knows, as the process is very cost and non-effective to compare with the hydrometallurgical activities. So we also in our project developed the urban mining marketplace, and this is a web platform for platinum group metals and photovoltaic materials circulation. Will give the idea and the view about how this circulating, how over this material circulating. And one of our activity also is focusing on empowering less developing regions by building industrial leaderships and circular growth access Europe. This is a very briefly introduction, let's say, but now let's move to the next slide. This is our consortium. It's quite, as you see on the slide, it's quite a big consortium. On our board is 19 partners from 10 countries and 15 regions. 11 partners belongs to the less development region. And this consortium was built on these actors, which are also very active in partnerships: S3, TSSP, Vanguard Initiative, AIT Raw Materials Kits, VF Forum, and so on. And we go together to build the first urban mine innovation ecosystem in Europe, as I said. What is the very important that this ecosystem is to deliver large-scale demonstration and the structure for this value chains in a view and based on the Circular Raw Materials Act, Green Deal, and Circular Action Plan. And what we would like to demonstrate and as an efficient output of our activity comes out from the 4 chains. It is to recover 80 to 99% of a range of strategic raw materials, and we will see how this activity will go on in accordance to our project's activities. What are our objectives? Our objectives we could conclude in the 5 points. The first one is building the first industrial-led hydrometallurgy network based on LDR, low development regions. This is the hydromet triangle. As the second objective is to scaling 15 innovation investments to reach TRL maximum, let's say TRL 9 and expand. And next one is putting the less developed regions in the lead of the portfolio, developing 4 interregional strategic raw materials value chains based on LDR, and centralizing interregional coordination of value chains and laboratories. By the way, by the building some kind of a platforms and information exchange. On this slide, let's say from the one for the objective number 4, which is developing 4 interregional value chains, as you see here on the slide. This is on this picture, we see 4 different lines. What is our, let's say, view? How in this 4 different lines? First one line is a battery. Hold the process of the battery. The second line is the platinum metals and copper. Line number 3. This is the first line here. It's very small, but I hope that you will see in my presentation everything in a more detailed. Second line, this is platinum metals and copper line. Number 4 line is number 3 line is raw earth elements recovery from the electricity equipment, and next line this strategic raw materials recovery from the white goods. What is very important that all of these lines is going through the 4, as I said at the beginning, 4 activities, like the 4 activities which is connected for the collection, dissemination, pre-processing, and finally to the hydrometallurgy process. All demonstrations are improved jointly, but last one company and one RTO, each in a tech transfer approach, while a clear emphasis on the cross-regional tandems. Here, for the first urban mining, 4 urban mines included 4 developing countries, less developing countries, Poland, Greece, Portugal, and Slovenia, and 6 LDR in the field of the value chain and urban mines. The triangle, the METIUM create, let's say in our product, we will create the hydromet triangle, which is, as you see on this picture, the first interregional hydromet triangle, which is connecting hydrometallurgical capabilities across the European Union regions, will coordinate, as a project, we will coordinate those regular hubs and organize exchange of the best practice as well as the inter-laboratory coordination. This will be work like that. METIUM will invest in key hydrometallurgical demonstration in the low development countries and connect them to each other and to their respective value chains. This is one of the very key important out of our activity, which is, as I said, connecting transition regions, more developing regions, and less developing regions, as we see on this on this picture. The next, let's say, maybe not the second, but the next, our priority of our activity is the scaling up 15 innovation investments to reach TRL 9 level and expand. expand. And this is here giving all this on this activity is giving here on this picture. So the innovation, the key innovation will be implemented in whole 4 value changes, and those are based on the industrial reality of the urban mining and 15 mature demonstrations to address those challenges in efficient and environmentally friendly way were identified. Very important part of our activity, having those innovations will be developed and implemented in every part of this kind of our activity in accordance to the 4 chain of our project for of our project cross-border strategic raw materials activities. Next one, putting less developing regions into the portfolio. And this is the reinforce and the growth of innovation and industrial capabilities in less developing regions. It was convinced to not as a portfolio, but as a chain of industrial investment needed to make the European urban mining a reality, involving this less developing regions as the one of the crucial point of our activity. Within this context and in the context of more developing European regions, less developed regions have long been missing, let's say, a form of support in infrastructure. So in accordance to consolidate side streams as well as meaningful plans and facilities to valorize urban mining waste. Companies from the less developing regions will be taken the lead of coordination, so across this value chains of strategic raw materials, while the project itself is coordinated by a leading RTO from the less developing regions. Next of our goal, centralizing interregional coordination of value chains and laboratories. As I mentioned before, in accordance to our project, we will develop the interlaboratory platform, which will proceed with the comparison on various materials and protocols to ensure consistent results across the segments of each chain, of each 4 chain. It will focus on the quality assurance, method harmonization, regulatory compliance, and continuous improvements. So, as you see here on this picture, is giving holders 4 points of this activity of this interlaboratory platform. And the Hydromet platform, the second one, the platform were implemented activities, 3 activities line, demonstrating servicing to support the hydrometallurgical processes of each the scaling up technology, hydrometallurgical scale up exercises, experience sharing regarding best practice of hydrometallurgical and methods of scale up, hydrometallurgical technologies into the industrial capabilities and processes, sustainability analysis, and so on about the hydrometallurgical issues. The next presentation will be given by the one of our partners from Greece Monolites. What is the next? This slide is giving the whole picture of our SRM, strategic raw materials value chain, which is valorizing regional urban mines from less developed countries, which is building upon leading edge technologies. And looking at the first line, let's say, this is divided for the following phases of the activity. Here on this picture, we see all the connections between the processes which are going in a different part of the value chain, from the beginning to the end. Let's say to receiving the strategic raw materials, and the phases are like this, covering whole of these 4 lines. First, phase 1, this is the efficient collection and sorting, taking account the first line value chain concerning the batteries. There are the 2 key feed sources of electromobility of urban mines, which is in Greece and in Poland. When we go to the phase number 2, so this is the advanced sorting and dismelting part of the activity. Phase 3, which is not just visibly put it here, but it's very important. This is one of our activity, which is focusing on using the mobile shredding model shredding. So this is novel mobile and modular shredding units, which we would like to use as the first step, as one of the step of the value chain. Phase number 4, wet processing, and this is advanced. When you are talking about this battery line, the wet processing, one of their activity will focus on this. Develop the advanced water treatment system, incorporated solvent recovery, plus innovative membrane filtration. And this kind of the system will aim to produce the best quality, let's say, best quality black mass, which will go to the next step, to the hydrometallurgy process. And the phase number 5, which is the end of the process, this hydrometallurgy scale-up, or let's say hydrometallurgy issues. And in the whole of this different parts of this activity, we will develop and scale up this one in accordance to our METIUM project. How it is everything construct in one project work. Here we see this our work plans, including the work packages. We have, as you see here, 7 work packages, which is covering all the activity of the project. Work plan includes 3 demonstration and scale-ups work packages. This is the 3, 4, and 5, supported by work packages number 1, 2, 6, and 7. And it's as you see, one of the important, very important, is work packages number 3. This is focusing on the dismelting activities. And the next one, the work package number 4, is the demonstrators that optimize the concentration. And 5, work packages number 5, which is developed by our next speaker, Monolites, is focusing on the hydrometallurgy processes and scaling up these activities as well. This is how it looks, our project, let's say, idea of the implementation. in accordance to the work packages and hold this METIUM work plan. So going to the final of 2 slides of my presentation, would like to say what is the transnational dimension of the METIUM project. In the project phases, as you see here in the 7 points, on this transnational dimensions covering the 7 points or 8, create 4 reliable value chains, sorting. The next one is consolidate inter-regional urban mine ecosystem at European level, establish a coordination structure of to align and integrate both technological and industrial capabilities across 4 value chains, invest in 15 joint Terrell 6, more demonstrations, drive the scale up of leading edge technologies across 3 METIUM segments, position low development regions in the lead of the strategic raw materials value chains to foster the connection to EU value chain as well as each transfer and so on. Set up at the end is the setup of the first hydrometallurgical triangle, as I mentioned before. And what is the transnational dimension post-project activities? This is given into my next slide. Set a percentage and the best practice to expand the model to whole European Union regions across all strategic raw materials areas. Building based on the hydromet triangle and existing value chains consolidated during this our 36 mine activities of the METIUM projects, and ensure the treatment plants will be replicable all over the Europe, and continuous regional authorities and stakeholders. This mentioned at the beginning, AFL and WEEE forum together with other activities and including my institute will implement activities to structure the interregional system of Uruguay mining innovation developed. This is the, thank you very much for your attention. This is a very brief information about our activity, which is counting for this 36 months of our activity, including 19 different partners. The project is not so is very interesting and not so easy to implement because of the lot of the parties and lot of the activities in every of the value chains. Which this what I would like to back here. This is the, let's say, the heart of our activity, giving on this picture how everything is going on and who is responsible for which part of this activity in our METIUM project value chain line, which is our, as I said, our main activities on this project. Thank you very much for the time and for being in here to share with my presentation. Thank you.
Thank you, Marek, for the excellent explanation of what the project is about. Now, from some more high picture of these activities, we will go to one company, which is indeed a partner in both METIUM and even closer. So it's also bridging a bit the presentation we just heard to the next presentation. But let's see something more in practice. Hi, Anastasia. The floor is yours for your messages.
Thank you very much. Good morning. I assume, yes, I can see now my presentation. Okay, thank you. My name is Anastasia Moscovi. I'm head of Research and Innovation Department of Monolithos company, and we have been involved in several projects by developing hydrometallurgical processes for recycling critical and strategic raw materials. And this is the reason why we are here, and I would like to thank also the organizers for these invitations. As a company, we are located in Athens, in Greece, and we have both commercial activities by producing automotive catalysts, but also research and innovation activities for developing recycling processes, pre-process of secondary raw materials, but also integrated catalytic systems, not only for after-treatment systems in automotive industry, but also other applications. Namely, we have 3 pillars of activities in the research and innovation activities, which the first one is the nanocatalyst development for several applications, such as emission control, vulcanization catalysts, and photocatalysts. Electrocatalysts for fuel cells and electrolyzers, and we have a waste valorization division for collecting, pretreatment, and recycling several metals from end-of-life sources such as rare earths from permanent magnets, platinum group metals from electrocatalyst and automotive catalyst, lithium, manganese, nickel, and cobalt from batteries, LFP and NMC, gallium, germanium, and indium from electronic waste sensors, etc. But we also follow the net waste principle, using the solid residue, the rest of the material that it is being used, it is being collected after the recycling for obtaining geopolymerization. These technologies are being overlapped, but they are separate, but also overlap in some cases where the material that we develop, they are also being recycled, and vice versa. We collect materials in order to recover the metals and produce new ones. All these activities and technologies, either for recycling or for nanocatalyst development, have been co-funded by EIT, European Institute of Technology, and Horizon projects, separated per category. For nanocatalyst development, electrocatalyst, non-emission nanocatalyst, critical and strategic raw materials recovery from fuel cells, batteries, electronic waste, PV panels, mining tailings, etc. We also participate as task partners or work package leaders, but even we coordinate some projects related mainly to nanocatalyst development, but also recycling by integrated AI principles in the sorting step in order to increase the efficiency of the recycling rate. Another pillar are the training activities, the training projects that we participate in order to develop modules, courses, lessons, or lectures with all the information results from our research and innovation activities. Anything that it is related with platinum group metals, for example, or recycling or hydrometallurgy, or hydrothermal synthesis of nanocatalysts, each and every of them in the frame of a circular economy model. We have a very well equipped industrial laboratory, which means that we produce components in scale of kilos per batch per day. We have equipment for physicochemical analysis of the material. as a quality control, but also monitoring the development steps. But we also have equipment for making assessment of the performance of the materials. For example, we are developing a new electrocatalyst. We are measuring the electrocatalytic activity of these materials. If we are developing a catalyst for emission control, we are measuring directly on the car with gas analyzers the performance of the catalyst on the gases transformation. We have analytical equipment in order to make all the measurements in-house, saving time, unless there is any exceptional measurement that needs to be subcontracted or collaborate with external partners. The main process, the main activities, the main steps that we follow in order to finally apply hydrometallurgy is by collecting end-of-life materials. We identify which of them contain critical or strategic raw materials. Then we have an extended network of collaborators. We collect the material and then we perform the dismantling, starting to downgrade the device in components that can be pre-processed and treated. Then the material of interest, the one that contains highly concentration of critical raw materials, it is downgraded even more in fine powder in order to be subjected in a hydrometallurgical process. Then it is diluted in chlorine-based media. The metals are being solubilized, and then we get a pregnant solution, the yellowish ones that you see in the scale, in the slide, containing all the metals that have been dissolved. Finally, either by precipitation or solvent extraction or other purification techniques, we can get the metals with high purity out of the solution. And of course, we identify the purity and the recovery rate with physicochemical characterization. In our case, we use mainly XRF and ICP analysis. We have developed and designed this method in order to have the least possible waste that are being generated from the process, use low acidity solutions in order to avoid the environmental impact, the high environmental impact. The method is quite flexible and versatile, which means that can be adjusted in different kind of streams. Co-extractors extract selectively metals from the materials of interest. And we are talking about a system of hydrochloric acid and the hydrogen peroxide as an oxidizing agent in low acidity, short leading time, less than 4 hours, and low temperature of operation, less than 70 Celsius degrees, which is in contrast with high temperatures that are being used in pyrometallurgy. Okay. So this process and the whole process, all the steps are being have been applied by monolithos in several end-of-life streams. We have collected permanent magnets from electric motors, autocatalysts from conventional or hybrid cars, membrane electrode assemblies, components that contain electrocatalysts, platinum group metals from fuel cells or electrolyzers, batteries, e-wastes, namely sensors or PCBs or other electronic components, solar panels, and waste byproducts by mining or a recycling process in large scale in industry. What we have concluded so far is in leaching process by using hydrometallurgy, the highest quantity of the metals is being extracted, if not the total amount of the metals. What defines the recovery rate in these steps are the pre-treatment process that takes place before the leaching, before applying hydrometallurgy. The pre-treatment, the pre-process, the downsizing of the materials, if a reduction of the components it is needed, reduction of the metals, thermal treatment or mechanical treatment. This is what defines, or also it is very critical for the recovery rate of the metals. So we have concluded that the streams should be separated, not avoiding cross-contamination from one stream to the other, in order to have the purest possible streams and increase the efficiency of the recovery during the leaching process. Otherwise, by not having a proper sorting of these streams, metals contaminate all the streams, between them, and finally we have a multi-metal component that we cannot selectively extract the metals. In our case, Monolithos is coordinating a European funding project, an Horizon project, whereby integrating the AI principles, meaning training a robotic arm with physicochemical characteristics of components. We treat this robotic arm to sort the materials per metal or per stream, which means that finally we will get streams with the least possible metals to be extracted, and the same pretreatment procedure that will be applied and followed. We have applied so far this method in fuel cell engine from a fuel cell cars that burn hydrogen in order to move. We have collected end-of-life hydrogen engines, and we have started to dismantle from the engine to the individual components. We follow a very detailed process for dismantling in order not to harm the components, and that way we can increase the recyclability of the whole material, of the whole engine, for example, if we can recycle and reuse or repurpose most of the components that they are contained in this device. And finally, we get the components out of the engine, and one by one, they are being subjected to hydrometallurgy in order for the metals to be extracted. That will be also the case in two projects that Monolithos is participating as a partner, bringing the expertise of recycling and the hydrometallurgical process in METIUM, as already described previously, but even closer. The basic principle is the same. Materials will be collected, pre-treated, and strategic or critical raw materials for European Union will be recycled and recovered. The difference between the two projects is that we are focusing on different metals. In the case of METIUM, copper and aluminium will be recovered by PV panels, but in the case of even closer, germanium, gallium, and indium will be recovered from electronic devices, PCBs, and antennas. So the process is the same, the source varies. So either from washing machines motors or from PV panels, they will be subjected in a pretreatment process, which means that from the initial part, we will downsize the material because they cannot be directly dissolved as they are. They will be pre-processed, homogenized, define where exactly the metals and in which concentration. If any other of pretreatment is required, either thermal or flotation to remove non-metallic parts will also be applied. But finally, they will be subjected in a leaching process. All the metals will be dissolved in a solution, and finally, either with precipitation, separation, or solvent extraction, they will be removed and recovered from these sources. In even closer, recycling of industrial and defense sector e-waste will be applied, meaning sensors or drones. We are planning, and we will focus in recovering gallium, germanium, and indium with this flexible hydrometallurgical process, developing a secure digital product passport, which means that data will be collected through the whole process from the pretreatment to the leaching and the recovery rate of the metal. And of course, at the end, we will establish a pilot plan and design recovery units that can be installed in different places. So the main principles, they are more or less the same. We identify the stream, the metals in the stream, the concentration of the materials in the components, and the same process with variations, of course, in the parameters. Adjusting and tuning the parameters will be applied for extracting the metals either selectively or co-extracted from the sources. But where we can find these materials, the secondary sources, either from scraps, from wafer fabrication, microchips, an electronic device. All of us, we have several electronic, from microelectronic or bigger electronic device at home that have been, that we do not even know where these devices remain in the house. End-of-life data center hardware. If we want to increase the capacity of a hardware, we increase the amount of the metals that they contain. Automotive electronics and the industrial and medical equipment. Antennas and e-waste will be collected, dismantled, downgraded and downsized in powder form, and finally, after metal detection, will be subjected into hydrometallurgical process for extracting gallium and germanium and indium. By adjusting the parameters of time, leading time, temperature, concentration, acidity of hydrochloric acid or the oxidizing agent, we are aiming in and we are focusing in extracting the maximum out of these metals, of course, and in high purity. The least possible purities that can be obtained. Of course, with incorporating all the equipment, the industrial and laboratory equipment that we have in our facilities for the pre-process, from crushers, milling units with ball mill, hammer mill, etc. Anything that it is required with respect to the hardness of the materials that can be downsized. Analytical equipment that it's been calibrated for the specific metals and the specific matrix to have the most accurate measurements for the metals. And then mixer settlers and reactors in different scale in order to develop the method and then increase the capacity and scaling up the process in semi-pilot or pre-industrial units. We have all the equipment that can be used, combined and adjusted to design and scaling up the process, either for the pre-process or the hydrometallurgy. We have units from 0.5 liters to 1 cubic meter, with an adjunct filtration system, but also in case where simple hydrometallurgy is not sufficient, we also have microwave hydrometallurgy pilot unit, the first ever designed and installed in the world, with several reactors working in a sequence, in parallel, treating materials of PV panels, automotive catalysts, etc., for recovering metals, but also nucleation systems, electro-crystallization system for obtaining the metals out of the leachate solution. Monolithos has developed, as I already said, technology, single step. It is considered single step because we do not need exceptional pretreatment other than mechanical treatment and a good sorting in advance. It is quite simple, I would say. Not exceptional reagents are being required for the metal extraction and solubilization in the solution. And the conditions that this process takes place can be applied in industry, can be applied in several reactors, in several batches. Leading time is quite short. The method is flexible and has much lower environmental impact than the conventional pyrometallurgy that is being used in such cases. I would be very happy if you have any question. I would be very happy to answer. Otherwise, you can visit our site. It is Innovation Monolithos site. You can see more details. You can find more details about the recycling and hydrometallurgy projects and the processes. But also you can contact us in the email that you see on the bottom right. Thank you very much.
Thank you so much, Anastasia. It's really different to see the pictures of the processes happening rather than only the slides of the presentation. So I think your contribution to this event is quite significant. Thank you. I will, since looking at the time, I will quickly go into the presentation of, yes. So first of all, it's the same project, just that the logo that you've seen before was the one at the proposal stage, but now we have a new communication team and we decided to change the logo. So but this will be the logo of the project from now onwards. And indeed, it's another I3 project, similar, funded actually by the same call that funded the METIUM project. And it's co-funded by the European Commission, of course, by EISMEA, but the total, indeed, as we were talking about before, the key materials at risks that we identified on dependencies, especially from East European countries, East Asian countries, and the USA are silicon, gallium, indium, and germanium. The project focuses on the three different stages. We first focus on indeed mapping. We are collaborating with something like 12 different waste managers from countries like Finland and Slovakia, to countries and regions like Aruba and Azores Islands. And there, of course, we have to map where is the semiconductors rich waste, make sure that we improve the collection and the preprocessing so that both can go in the right recycling stage. We saw before where the project will send the gallium, indium, and germanium rich streams to Monolithos, while the silicon will mainly be extracted from solar panels, and I will touch this later on. Then, of course, we enter back into the manufacturing. One thing that is true indeed is that has been mentioned before, while there are quite strong semiconductors, chips production streams in the Closer project, which is another I3 I've prepared in the past, and it's still active. It's in its second year right now. That project lacked a strong silicon production stream, and that's where Even Closer comes in on the manufacturing stage. We are 44 partners. It's coordinated by the University of Calabria. Indeed, it's 36 months, and it's starting on the 1st of November. That's also the reason why there is not yet a branded presentation. I apologize for that. But indeed, again, the main objective is to integrate as many less developed regions as possible. Now, of course, you don't see on the picture the Azores Islands and Aruba, but they're also there. We have 4 pillars of activities. The first one I was touching on already, both mapping and tracking. We are making different GIS maps on where in Calabria, Sicily, Slovakia, Azores, Aruba, Finland, and also in the Netherlands, these semiconductors-rich waste streams are. Of course, we will also collaborate with industrial partners, especially from the automotive sector. For example, we have provision of waste from both Aumovio, which is now the new name of Continental's electronics department, and also from Borg, which is the biggest remanufacturer of cars in Europe. All of this will be also tracked. So we are exploiting an open source digital product passport solution that one of the partners has developed already in previous projects. We are integrating it with Europe's largest recycling platform made by Circle, so that the different waste coming from the waste managers at different stages of processing can be tracked and can become available for the market to actually find its demand, find someone that actually wants that material for processing. Then we are working a lot to improve the sorting and processing technologies. That's an initiative led by SEA. It's the Commissariat de l'Énergie SEA, the large French research center that I'm sure if you deal with European projects, you know them as well. It's mainly a system between camera vision and spectroscopy, X-rays combined, that would allow to separate waste much better. And the first part of the project will develop it, and the second part of the project will install it at least to the premises of one of the waste managers we saw before. And then we are also focusing a lot on local communities for repairing and refurbishing what we can avoid to recycle. The second one, both on PCBs and gallium. I will not talk about the gallium, indium, and germanium from the civil scrap one, but because this has already been touched in the previous presentation, but about PCBs, we are reinventing them in a way that we are both repairing them, but also finding a way to use this recycled silicon and recycled tin and lead to make PCBs containing a high amount of recycled content. And the project will assemble by the end of the project 25 high-quality PCBs using 300 kilograms of reclaimed materials. On the solar panels, since this is indeed the part of silicon, so we take it from solar panels, as I was saying. We already have some partners that are able to, through delamination of the solar panel, to get to a 99.5, 99.6 material recovery, but also purification, because 95 is an old number. We're already at 99.5. And then this silicon powder will feed a whole innovative, but also a stream of technologies, infrastructure, and competences that the US lost, because the way to make silicon ingots, silicon buffers, and so on, it's something that we were good in before, when companies closed, and now we need them back because the geopolitical situation changed. So from that silicon powder, we will have all the different steps from monosilicon, polysilicon, up to the point where we are going to create a silicon diode, a silicon element to put on a PCB that will then be tested functionality-wise in a real by a real company, and if it works, if we're able to make this as economic as possible, let's say, it will then really shape the European supply chain, at least variegate the provision of silicon-based components for the semiconductor sector. So I think I've touched on this. Another pillar we have is indeed to build the ecosystem, both policy-wise, where we will have policy labs. We will touch on collaborating with the different regions from the project, collaborating with the different companies. We will have continuous labs, continuous workshops to feed the policymakers that are willing to create a better environment for the growth of this circular supply chains we are activating. Then, of course, we are also looking at what else is the EU missing right now. What else is the which other technologies, which other capabilities are we missing? And that's why we have a full work package dedicated to incubating new startups. 45 startups will be selected, mentored, and scaled up. The calls, so it's 15 per year. The call for these startups will be global, in fact, with a mandate to establish a legal entity in the European Union through by the end of the incubation program. So that's really a way that we are trying to reattract some talent and reattract some technology that we have lost in the EU. And then finally, a lot of these supply chains, which have 6 or more steps, depending on which one you are looking at, and in each location of this, you have also different inter-regional movements. Well, it creates quite a lot of a logistic problem and challenge, at least. And for that reason, we are looking to establish in a less developed region, because that's what we want, following the cohesion policy of the European Union, a logistic hub for the different movements of the waste at different stages in the EU. As we saw before, this project is linked to the Closer project, if for anything, by the fact that the same person that prepared Closer prepared even Closer, and by the fact that several tasks are designed to be synergic. Of course, it's up to the coordination entities and up to the different partners to put this in practice, but the plan was to manage them in synergy, and so to maximize the budget of the European Commission and to not lose that into too many similar activities, because of course every project has its own communication work package, its own policy work package, and so on. And so we wanted to make this as efficient as possible, but also for the input and output of the different materials, as I was explaining before. Finally, we have the skills education part of the project, where we are looking at creating a massive open online course for something that will allow us to gain the right workforce to run these different value chain position plans and so on, because the moment you import from outside or you recreate some capability, you also need the people able to deal with it. We will support the whole project in commercialization. In fact, we have as a strong KPI the need for additional 26 million on top of the 14 million the European project already has, 10 of which from the Commission, 4 from the different partners. But yes, additional 26 million from either of the European projects, but mainly for angel investors, other kind of investors, banks, and so on. So I will maybe be quick because the time is running, but yes, we are trying to make this as replicable as possible. We are not looking at this as a single project, but as a strategic investment in Europe industrial's future, turning today's West into tomorrow's technology sovereignty. So thank you very much. And of course, now we can have the last 5 minutes, unfortunately, for questions, which I have something like 200 questions in my mind for all the speakers, but yeah. I think we can call everyone back. Sorry, I tried to be quick so that we had still 5 minutes at least to talk among each other. Before I ask something to you, do you have any question for each other? Did any presentation of anyone else raised your made you wonder about something?
I don't have the particular questions to each of us, but I would like to say that I'm very impressed with the whole of this presentations, and especially this gives me some kind of a summary why all these projects are, let's say, why all these projects are very important and crucial for the procurement of strategic raw materials, and from the second hand, this whole of our projects are very important from EU regions, especially from the less developed regions. My project, let's say, not mine, sorry, of course not mine, but the project METIUM, which is managed by my institution, Institute of Non-Ferrous Metals, and together we are cooperating with the monolites, which is also have the presentation here. It's very crucial from the strategic point of view, from the, let's say, strategic raw materials issues, because it reduces European Union strategic dependency on the different kind of the world, and creates an alternative kind of activity for primary mining. We are demonstrating in accordance to our project and several recovery, and including the innovations, implementations, and so on, which go on the TRL 9 level. And the project is also crucial from the procurement of strategic raw materials, because of enables circular value chains across the Europe, and builds critical mass through the European Union-wide urban mining marketplace. This is one of the our key point, which is I would like to underline, and this is what I also prepared, let's say, for myself for the final discussion, let's say. But whole of our projects are focusing on the same issue which I mentioned before. So I'm very, very happy to be here and to present this, what the METIUM project will develop during this 36 months of our activity. And I was very satisfied to see and hear about the UNITAR project, and your Luca project activity is already done. So thanks a lot.
Thank you, Marek. Maybe one question, because indeed our projects, of course, we also mentioned Closer today, but which is at the beginning of its second year, but both Even Closer and METIUM are really just very fresh. However, we have one project which is almost at its end, and I'm wondering what we can, as new fresh projects, take from the lessons and from the results that that project has developed. And maybe one question that I already had after some presentation is, we indeed touch a lot about strategic materials, critical raw materials, and you have done both a methodology and applied it to a lot of the strategic and critical raw material, Julia. But you see in our project in Even Closer, that we also touch a lot about on indium. Indium is a very important material. The moment you start looking at the supply chains of production of semiconductors, for which actually it has been discussed inside the European Union, should it be a critical raw material, should it not be? But right now it's not. How easy, or maybe is it possible to use the methodology you guys have developed to also analyze other materials, and how could that happen?
Thanks a lot, Luca, for the reflection. And I would say definitely yes, because we are not just focusing on critical raw materials, or let's say what is classified nowadays as critical raw materials and strategic raw materials, but also on secondary raw materials more in general. So we have data also concerning material fraction, ferrous metal, plastic. So also indium could definitely be following the same methodology. And I think also, to answer what you were, or let's say to provide a comment on what you were asking on what your project, which are new, can take from, let's say, almost closed or at a final stage project, is to develop approaches and methods that can be long life sustained and that are flexible enough also to follow the changes that will be upcoming. We know that the list of critical raw materials will be updated in the next years. We don't know if any other criticalities or other criteria will be introduced. So I think for any of the activities that you're planning, it's important to foresee that these changes might happen, and your approaches, your method, your technology should also be ready to somehow adjust to that. So indium is also part of our analysis. So yes, our methodology could be applied to indium as well.
Thank you so much for the reply.
And maybe if I also had a comment, which is in the same line of what Marek says. It was very impressive to me to see like your project that are much more, let's say, vertical, industry driven, much more technical, while from FutuRaM side, we are more on the data analysis, data production, collection and further elaboration of data research. And I think it's important to see and to notice and to ensure that these two different sides are going hand in hand somehow, and they can fit very nicely and take a lot from each other, I think. So it's also great to have more occasion like this one that we have today of contact points, just to ensure that we are all working on the same direction somehow.
For sure. I think it's fundamental that both approaches are. I mean, you can if you only leave things to companies without an idea of a general picture, but data can give you. You risk to lose the opportunity to make something with an industrial strategy. Now, of course, it's problematic. It has always been a challenge at European level to do something with an industrial strategy. But I think what the I3 program allows us to do, focusing on TRL 7 to 9, and having these large networks of companies that we require, because one of the requirements of the I3 program is to have 70% of the budget to small and medium enterprises, which brings you to have to connect companies and lead it in the way both Marek and I have shown a bit. Well, once you do that, if you don't have data, if you don't have the input from analysis like yours, you risk to not do the right thing, or at least not to suggest or connect companies in the right way. So I think that's why I really was interested in hearing from you, and I was following your projects in a while, and I'm very happy we had the opportunity to both share this stage today.
Can I make one last comment based on what you said? If we can apply the methods in other sources or streams for indium, what we have seen, not only as monolithos, but also as a member of METIUM and even closer, there are several processes from the pretreatment to the recycling of the metals, and they are being designed quite flexibly. Quite flexible means that they are flexible in the scale that they can be applied, but also by tuning or adjusting some parameters, it can be applied in several different streams or byproducts, because one asset of the industry is that we are recycling the materials, but the side products that are being obtained and collected after the end of the recycling, they are still worth to be recycled. If these processes, these methods can be adjusted, combined, altered, changed, whatever, we have multiple of methods in both projects. Also, these byproducts or other streams, if indium is even in lower concentrations, materials, streams can be pre-concentrated and then metals can be extracted.
Yeah.
So I think it is the next step to design all the processes in that way that can be applied in big scales, in several scales, but also in several streams. For industry, this is a benefit.
Absolutely. I think also leading some policymakers discussion I had recently, there is a lack of understanding of how flexible these methods can be, and to show, in this case, through the example of monoliths, but companies doing hydrometallurgical processes, doing this kind of processes could easily adapt to other streams. It's something that should be taken into account when doing policymakers and understanding how to, as fast as possible, develop the right infrastructure. Now,
Yes.
that being said, we are 5 minutes late on the agenda, and I'm so sorry to close it now. I would really love to keep, and I hope I will keep talking with all of you in the future, but I have to close the webinar, so we have to go offline. And thank you very much, Julia. Thank you very much, Marek. Thank you very much, Anastasia. It was a great session, and I loved all of the presentation, and it was an honor to moderate it. Have a nice day. Bye-bye.
Have a nice day. Thank you very much.
Thank you.